Shor's algorithm allows us to effectively search for a period of some periodic function. Now, how does this help us with factoring? Let's see. Again, we have a big composite number n, which consists of two different primes. And we randomly choose some number a smaller than n and coprime to it. And if we choose randomly number a and it appears to be not coprime to n, then we don't need all the following, since we can just compute the greatest common divisor of a and n, and if it is not 1, it will be one of these numbers, p or q. So a and n are relatively prime, and we define function fa like this. Like it maps integer number x, natural number x, to a raised to the power x modulo n. And all such a's, all such numbers less than n and coprime to it, form a finite group under modulo n. So there exists such smallest number r, so that if we raise a in the power r, we get 1 modulo n. And r is the smallest such integer. And this r has to be also the period of this function fa, since if we compute a in the power x plus r modulo n, it equals to a in the power x multiplied by a in the power r, which is 1. And we get just a in the power x modulo n. Okay, so this r is a period of this function, and you remember that Shor's algorithm allows us to search for period. So imagine that we employed Shor's algorithm, and for this function fa defined by this random number a, we found this value r, its period. Now let's assume that we are lucky today and this r happens to be even. Now what does it give us? Well, let's rewrite this identity like this. And the power r minus 1 equals to 0 modulo n. And since r is even, what we have here is the difference of squares. And everybody knows what to do with difference of squares when you see one. You decompose it. So we decompose it like this. R a and r divided by 2 plus 1, and the same minus 1, and this equals to 0 modulo n. So this means that n divides this product. Now we can be sure that n does not divide this factor, because if this factor was divisible by n, that would mean that r in the power r divided by 2 equals to 1 modulo n. And this contradicts to our assumption that r is the smallest integer for which this identity holds. So this is obviously not true. And let's assume that we are even more lucky today, and this factor n also doesn't divide this factor. So we write it like this: a in the power r divided by 2 not equal minus 1 modulo n. So these are our assumptions, which depend on our luck. And in this case, we have two factors. N divides their product, but does not divide any of these factors separately. This means that the factors of n itself, p and q, are situated in a different terms, factors here. And we can search for it by Euclidean algorithm. So this is all wonderful and exciting, but we must not forget that we employed some luck along with this reasoning, and now we have to estimate how much luck do we really need. So how much luck do we need for those assumptions to be true? So what were our assumptions? The first was that r is even, and the second was this. Well, let's introduce two new numbers. A1 is A in the field Z modulo P, and A2 is A in the field Z modulo Q. And we are going to introduce also the orders for these numbers in those fields. R1 would be the smallest number, such as A1 in the power R1 equals to 1 modulo P, and R2 is the smallest such a natural number, that A2 in the power R2 equals to 1 modulo Q. Okay, now we have these that are in the power R. R in the power R equals to 1 modulo PQ, and we can conclude that A in the power R equals to 1 modulo P also. And this R and this A in this field is A1. So A1 in the power R equals to 1 modulo P. And from this and this, we can conclude that R is multiple of R1. And the same reasoning for the field ZQ gives us that R is a multiple of R2. Okay, even more. Let's consider any number S, which is also multiple of these both numbers, R1 and R2. Then A modulo A in the power S equals to 1 modulo P, and also it equals to 1 modulo Q at the same time, which we can write like A in the power S equals to P multiplied by some integer K1 plus 1 and at the same time A in the power S equals to Q multiplied by some integer K2 plus 1. And we are going to subtract these equalities one from other to get this pk1 equals to qk2. Now, q does not divide p. That means that q must to divide k1. And then this equation we can rewrite like a in power s equals to pq, some integer which is k1 divided by q. So note this is integer, plus 1, which means that a in the power s equals to 1 modulo pq, which is n. So for any number which divides both r1, which is a multiple of both r1 and r2, it has also to be a multiple of r. And r is itself multiple of this r1 and r2, which means that r is the least common multiple of these numbers. Now let's decompose these two numbers, r1 and r2, like this. What I want to extract the powers of 2 in them. So we have, for r1, we have c1 as power for 2 in it, and for r2 we have c2. And we remember that r is the least common multiple of these two numbers. So this 2 in the power c1 multiplied by some odd integer, and 2 in the power c2 multiplied by another odd integer. And now let's assume that c1 and c2 are not equal. For example, c1 is bigger than c2. Then this least common multiple, r, would have, of course, it is a multiple of r2, so it will have r2 in it, in its factor representation. And also it will have at least 1, 2, because c1 is bigger than c2. And maybe some integer. Okay, what we see here is that r, in this case, when c1 is bigger than c2, or whatever, maybe c2 is bigger than c1, in this case, r is even, and our first condition is met. And more, if we have r in the power r, a in the power r divided by 2, this is a in the power r2 multiplied by some integer, and it is 1 modulo q, as we remember, which does not equal to minus 1 modulo q if q is bigger than 2. And this means that it also does not equal minus 1 modulo pq, and we see that the second condition is also met only if we have inequality of these powers of 2 in numbers r1 and r2. Now, how likely is that to have different powers of 2 in this representation of r1 and r2? The short answer is it is rather likely. It appears that these powers here in these numbers R1 and R2 tend to be greater than in ordinary random numbers. Let's see it for ourselves. So let's take a closer look at the fields ZP and Z modulo Q. Let's decompose P like this. So we have to extract the power of 2 in its closest neighbor, P minus 1. And S here is some odd number, and K is greater or equal to 1. And the same for ZQ. We have Q equal to 2 in some power L multiplied by some other odd integer plus 1. And L also greater or equal to 1. Okay, since ZP and ZQ are fields, they have primitive elements in them. Here we will call it B, and this element B generates the whole field. So the powers of B form all the elements of the field, and we have only P elements of this field, so the order of B would be P minus 1, which is 2 in power K multiplied by S. And this equals to 1 modulo P. Okay, now A1 is itself the element of this field, ZP. So it is B in some power, let's call it M. And we remember that A1 in power R1 is 1, and it is also B in power M R1, and is 1 modulo P. So we have this, and this means for us that M R1 is multiple of 2K S. And since A is a random number, for us M is also a random number. And the same reasoning here. Instead of M, we will have some N here, multiplied by R2 is multiple of 2 in the power L S1. Okay, the worst case for us here, if we have not multiple here, but this, if MR1 equals to 2 in the power K multiplied by S, and here NR2 equal to 2 in the power L S1. Because you already see that the oddity, the number of 2's in this R1 and R2 depend on number of 2's in these random numbers. And again, the worst case is if K equals to L and equals to 1. Because in this case, we would have the least number of variations for number of 2's in R2 and R1. For example, if M and N appear to be odd, then R1 and R2 would have exactly 1, 2 in them. And if both these m and n appear to be even, then R2 and R1 will be odd. So in this worst case, the probability that we are not lucky is the probability of that the randomly chosen numbers, two randomly chosen numbers, have the same oddity. And the probability of that is 1/2. And that means that with at least this probability, 1/2, we are lucky. And 1/2 doesn't sound too bad. So this, let it be the probability of our luck. And we can now proceed further to the quantum Fourier transform.